Hi everyone, this video is about prefix-free codes and the Kraft-Macmillan number. In the last video, we introduced the Kraft-Macmillan number for a code, and we showed that if that number is less than or equal to 1, then there exists a prefix-free code with the given parameters, that is n1 through n sub m. And that in turn implies that there is a uniquely decodable code with those same parameters. Now what we don't know is, well, what happens if k is strictly bigger than 1? So in the course of this video, we're going to establish, in fact, that all of these implications are reversible. That is, that k is less than or equal to 1 if and only if there exists a prefix-free code with the given parameters, which is true if and only if there exists a uniquely decodable code with the given parameters. So what this would tell us is that if k is bigger than 1, we're out of luck. To show that the implications on the previous slide are reversible, it suffices to show that any uniquely decodable code has a Kraft-Macmillan number that's less than or equal to 1. So to do that, we're going to introduce some new parameters, these q sub r of i's. So q sub r of I is going to denote the number of messages of length r back in S star that, when encoded, give messages of length I in the code alphabet T star. So another way to think of that is, if we encode all possible messages of length r, how many of the encoded messages are of length I? So note that q sub 1 of I is just simply the number of code words of length I. That is, q sub 1 of I is n sub I. Okay, here we have an example that we're going to talk about over the next couple of slides. So we have a specific alphabet S consisting of V, W, X, Y, and Z. Our code alphabet is going to be 0, 1, 2. So that means that our code is going to be a ternary code. And specifically, the ternary code sends V to 0, sends W to 1, sends X to the string 2, 0, Y to 2, 1, and Z to 2, 2. So first we're going to compute the value, or the Kraft-Macmillan number for this code. And then we're going to find q sub 1 of I for all values of I, q sub 2 of I for all values of I, and then we'll also find the value of q sub 3 of 5. So here we carry on with this example. We begin with the Kraft-Macmillan number. Since this is a ternary code, I know that it's n sub 1 over 3 plus n sub 2 over 9 up through n sub m over 3 to the m. So I just need to pull out what the parameters n1, n2, etc. are. So n1 is the number of code words of length 1, and I see that there are 2 of them, namely 0 and 1. So I get 2/3. Then I count the number of code words of length 3. I see there are, or excuse me, number of code words of length 2. I see there are 3 of them. So I write this down, and then there are no code words of any higher length. So my Kraft-Macmillan number is just 2/3 plus 3/9, which is equal to 1. All right, now we compute some of these new parameters, q sub r of I. So in B, we're computing q sub 1 of I for each value of I. So q sub 1 of 1 is the number of code words of length 1, and again, we saw that there are 2 of those. Q sub 1 of 2 is the number of code words of length 2. There are 3 of them. And then q sub 1 of I equals 0 whenever I is bigger than 2. Right? There are no code words of length 3 or of length 4 or of length 5, etc., etc. Okay, moving on to part C, we're going to be computing, let's first start with q sub 2 of 1. So what is this? So what we're doing is we're encoding all of the messages of length 2 back in S star, like for instance, VW and XY, all messages of length 2, and we're going to count how many of those, when encoded, have length 1. And the answer is that none of them have length 1, right? The very shortest length of an encoded message from S of length 2, the very shortest length would be 2, right? Like for instance, VW, that message when encoded becomes 01, which is of length 2. So there are no messages of length 2 in S star that when encoded to a string in T star have length 1. So what about q sub 2 of 2? So now we're looking for messages in S star that when they are encoded, messages of length 2 in S star, that when they are encoded, give us a coded message of length 2. And we see that really the only way that that can happen is if we put V's and W's together, right? If we put a V, for instance, together with an X, the coded message is 0 to 0, and that coded message has length longer than 2. So we see really that there are 4 ways to get an encoded message of length 2 from an original message of length 2. That would be encoding VV, VW, WV, and WW. All right, so now let's look at q sub 2 of 3. Now, what is that? Here we're encoding messages of length 2 in S star, and once we encode, we're going to count all the messages that in T star that are of length 3. For instance, if we were to take VX, that's a message of length 2. We encode it, and the encoded message would be 0 to 0, which is of length 3. So how many ways are there to do that? Well, the only way you can get something of length 3 is to put something of length 1 together with something of length 2. So there are 2 ways to pick something of length 1. There are 3 ways to pick something of length 2. And then the order that you put those things in matters, so you multiply by 2, and that product becomes 12. So q sub 2 of 3 is equal to 12. And then finally, q sub 2 of 4. So here we're looking at messages of length 2 in S star that get encoded to messages of length 4 over in T star. The only way that can happen is if you put a couple of these guys together. Okay, so X, Y, and Z. So I need a message of length 2 from those 3 letters. How many ways are there to do that? Well, there's 3 ways I can choose the first letter and 3 ways I can choose the second letter. So that gives 9 total ways to choose or to create a message of length 4 from an original message of length 2. Now, what about the other values of I? Well, q sub 2 of I is going to be 0 when I is bigger than 4. And what's the reason for that? Well, if I is 5, for instance, you're looking for a message of length 2 over an S star that gets encoded to a message of length 5. And that can't work out because, all of the code words are of length either 1 or 2. Okay, now we address the final part of this example, and that is computing q sub 3 of 5. So q sub 3 of 5, again, what is it that we're counting? So we are taking messages of length 3 from S star, like for instance, WXY or WZX, and we're encoding all those messages of length 3. And then once we encode them, we want to count all of those encoded messages that are of length 5. So how can you put 3 code words together to get a message of length 5? Well, the only way to do it is to choose 2 from here, right, to get something of length 4, and then also have something from here, which would give us something of length 1. So if we have 2 from there, that gives us length 4, plus another thing of length 1 gives us length 5. So how many ways can that be done? So if we're going to choose 2 things in order from the latter 3 code words, there are 3 squared ways to do that. And then if we're going to choose something of length 1, there are 2 ways to do that. But then we have to figure out where to place that code word of length 1 in relation to the 2 code words of length 2. Is it going to be at the front? Is it going to be in the middle, in between them? Or is it going to be at the end? So there are 3 choices to make there. And so at the end of the day, we get 54. So you can see that when we compute these q sub r of i's, things like this, for instance, there could be some relatively complicated counting problems for us to solve. So this could become an annoyance for us later. Our work on the previous slides showed us that computing these parameters q sub r of I is possibly an arduous task. And it turns out that there's an easier way to compute these parameters using what's called a generating polynomial, capital Q, which is defined like this. So if we use the code that we defined in the previous example, let's write down the generating polynomials capital Q sub 1 and capital Q sub 2. So capital Q sub 1, well, that's little q sub 1 of 1, which you might remember was 2, times x, plus capital or little q sub 1 of 2, which you might remember was 3, times x squared. And then all of the other little q sub 1s were equal to 0. So this thing here, this q sub 1, capital Q sub 1, that's the result. Okay, what about capital Q sub 2? Well, here again, we have to remember some little q's that we computed a little while ago. Little q sub 2 of 1 was equal to 0, so we get 0 x's. Little q sub 2 of 2 was equal to 4. Little q sub 2 of 3 was equal to 12. And little q sub 2 of 4 was equal to 9. And all of the other little q sub 2s were equal to 0. So that is what we've written down there is capital Q sub 2 of x. Okay, so that deals with part A. Now for part B, we computed little q sub 3 of 5 on the previous slide. What does that number tell us about capital Q sub 3? Well, little q sub 3 of 5 should be the coefficient of x to the 5th inside this polynomial, capital Q sub 3. Okay, now when we computed, back to part A again, when we computed capital Q sub 1 and capital Q sub 2, you might have noticed that Q sub 2 is the square of Q sub 1, right? So Q sub 1 of x, quantity squared, is equal to Q sub 2. And let's cube Q sub 1 of x now. So if you go out and do a little bit of calculation, what you'll find is that the cube of Q sub 1 of x is 8x cubed plus 36x to the 4th plus 54 x to the 5th plus 27x to the 6th. So you might be wondering, well, is capital Q sub 3 the cube of capital Q sub 1? Well, notice in part B, we determined that little q sub 3 of 5 should be the coefficient of x to the 5th inside of capital Q 3 of x. So I look down here, notice that when I cube q sub 1, I get a polynomial where the coefficient of x to the 5th is equal to 54. Well, you might remember that 54 was the value of little q sub 3 of 5. So this suggests that this might just be q sub 3 of x. So the conjecture that we might form from all of this is that if we want capital Q sub r of x and all of the coefficients that go along with it, then maybe all we have to do is take Q sub 1 of x and raise that polynomial to the rth power. Okay, now if that conjecture is true, we can compute little q sub 3 of 4 just at a glance, right? So remember, little q sub 3 of 4, that's the number of messages of length 3 back in S star that become encoded as messages of length 4 in T star. And instead of doing a bunch of counting, maybe we should just look at this polynomial that we just computed, which we are purporting is capital Q sub 3 of x. Little q sub 3 of 4 here should be the coefficient of x to the 4th in q sub 3 of x. So if our conjecture is correct, then this number, little q sub 3 of 4, without doing any work, counting work, should be 36. So it turns out that the conjecture on the previous slide is in fact true, that capital Q sub r of x is the rth power of the polynomial q sub 1 of x. Okay, that's great news because q sub 1 of x is relatively easy to compute, and then we can compute higher powers of that polynomial just by either using the multinomial theorem or by using a computer algebra system. And that allows us to compute all of these coefficients of q sub r rather easily. Like if I want little q sub 50 of 37, that is messages of length 50 in S star that encode to messages of length 37 in T star, instead of doing a bunch of weird counting arguments, all I have to do is take q sub 1 of x, this polynomial capital Q sub 1 of x, raise it to the 50th power, and then look at the coefficient of x to the 37th. So we're now going to use these parameters q sub r of I and the associated generating polynomials to prove something fairly important. So we're going to show that if we have a uniquely decodable code, then its Kraft-Macmillan number must be less than or equal to 1. To prove the theorem, we start by assuming that the size of the code alphabet is equal to b, and that m is the maximum length of a code word. Since the code is uniquely decodable, we know that q sub r of I is less than or equal to b to the I. So let's examine this statement for just a moment to see if we believe that. B sub I is the total number of distinct strings in T star of length I. Q sub R of I is the number of messages of length R back in S star that are encoded to strings of length I. If Q sub R of I were to exceed B to the I, then we would have to reuse some strings of length I. And we can't do that if our code is to be uniquely decodable. So q sub r of I must be less than or equal to b to the I. So another thing to notice is, since m is the maximum length of a code word, if we're going to encode a message in S star of length r, then the maximum possible length of that coded message would be r times m. So that means q sub r of r times m is the largest potentially non-zero coefficient in the polynomial capital Q sub r of x. So anyway, we're going to take our capital Q sub r of x and we're going to evaluate it at x equaling 1 over b. And when we do that, we obtain this expression right here, which terminates at q sub r of rm over b to the rm, because this q sub r of rm is the largest coefficient in capital Q sub r. Now, each one of these little q sub r's, like little q sub r of I, is less than or equal to b to the I. In particular, q sub r of 1 is less than or equal to b. Q sub 2 of r is less than or equal to b squared. And this is going to be less than or equal to b to the rm due to this inequality right here. So notice what that says is that capital Q sub r of 1 over b is less than or equal to b over b plus b squared over b squared plus and so on. But those are just ones, right? Capital Q sub r of 1 over b is now going to be less than or equal to 1 plus 1 plus 1 rm times. And so we conclude that whatever q sub r of 1 over b is, it must be less than or equal to r times m. Now, meanwhile, this expression in the middle, this sum, it looks a lot like the Kraft-Macmillan number. And in fact, it is exactly the Kraft-Macmillan number when r is equal to 1. That is, k is equal to capital Q sub 1 of 1 over b. So now we can use the counting principle that we had on the previous slide. We see that k to the r, It is the Kraft-Macmillan number raised to the rth power. By substitution is this q sub 1 of 1 over b raised to the rth power. But by the counting principle, that's q sub r of 1 over b. But remember, we just showed a moment ago that q sub r of 1 over b is less than or equal to r times m. So if we take this inequality and we divide all sides of it by r, we obtain k to the rth power over r is less than or equal to m for every possible value of r. Now, if it were true that k was bigger than 1, then this quotient actually tends to infinity as r goes to infinity. And that would contradict the fact that k to the r over r is less than or equal to this m always. That means that the Kraft-Macmillan number k must be less than or equal to 1. And that proves the theorem. Let's summarize now what we know about the Kraft-Macmillan number. From the earlier video, we knew that if k were less than or equal to 1, then that implies the existence of a prefix-free code with the parameters n sub 1 through n sub m. And that, in turn, implies the existence of a uniquely decodable code with the given parameters. But now, because of the material we covered in this video, we saw that this statement here implies that k is less than or equal to 1. And that means that instead of having a chain of implications beginning with k less than or equal to 1 and culminating with the existence of a uniquely decodable code, we have instead a collection of 3 equivalent statements. Now, another way to view this is if k happens to be bigger than 1, then we're just out of luck, right? If k is bigger than 1, then there is no prefix-free code and no uniquely decodable code with the given parameters.